Hello Brian, my name is Subrata Samanta and I am from IIT Kanpur. So I am a tutor for the physics subject. So in the previous few classes we have learned that the various charge distributions and how to calculate the electric due to those charge distributions. Okay. So today we will discuss the concept of electric flux and how to calculate the electric field using the Gauss law and the concept of electric flux. Okay. So to discuss the electric flux, let's first consider the flow of liquids, okay, through a small surface, and now I want to ask that what is the rate of the liquids, the flow of liquid. Okay, so basically let's first consider the flow of liquid, and that is closely related to the flux, electric flux. So let's first electric flux. Electric flux. So before we discussing the electric flux, so first let's consider a flow of liquid. So let's consider a flow of liquid velocity v vector, okay, and pass through a small surface that we denoted ds vector. Okay, so pass through a small surface okay, so ds vector. So basically draw the diagram that this one is the velocity of a liquid. We places we consider a small surface, the ds, okay, and the area vector is perpendicular to the surface, okay, is normal to the surface always, this is the ds vector. Okay. So in this case the velocity of the fluid is parallel to the normal to the surface. Okay. So v vector is parallel to ds vector. Okay. So you consider a surface that is perpendicular to the fluid flow, okay, the perpendicular to the flow of the fluid. Okay. Want to ask the questions that what is the rate of flow of liquid, flow of liquid. Okay. So before that, so the another question, the first one is that what is the volume occupied by the liquid in time dt. So what is the volume occupied by the liquid in time dt. So we consider a small time interval dt, okay, and calculate the volume occupied by the liquid in that time, and then we calculate the rate of the liquid, rate of the flow of liquid. Okay. So it is closely related to the flux, okay, electric flux. So first we consider the flux in case of liquid, okay, and then I will discuss the flux in case of electric field lines. Okay. Okay. So if you draw a diagram that again I think this is the v, the velocity of the fluid, and you consider the surface ds, okay, and the volume occupied by the liquid, okay, in time dt. So this is the ds vector, okay. Volume occupied by the liquid in time dt, okay. So is, so what is the length, okay. So because if you know that the surface area ds, so this ds vector dot the length, okay. So in dt time if the velocity is v, so the length one is v, times dt. Okay. So this is the length in dt time. Okay. So the total volume is ds, okay, times the length, okay, the distance, basically the distance covered by the fluid in time dt. So this one is v dt. So now since the v vector and the ds vector are parallel, so v parallel to the ds, so v dot ds, v ds cos, so 0 degree, right. So the intermediate angle 0 degree, so this one is v ds. Okay. So place that things here, so v, we get v ds dt. So that is the volume occupied by the liquid in time dt. So provided that the velocity vector and ds vector are parallel. Okay. So if this is not parallel, so there is a angle dependence theta. Okay. So if we consider this one is v, if we consider a surface tilted, the tilted surface. Okay. So that means the area vector always perpendicular to the surface. Okay. So and so this one is angle theta with the flow of liquid. So in this case, the volume occupied by the liquid in time dt is v ds dt cos theta, right. So there is a theta dependence, cos theta dependence comes into the picture. Okay. So then we will calculate the rate of flow of liquid. Okay. So the rate of flow of liquid, the rate of flow of liquid is given by the volume crossing the area per unit time. Okay. So volume crossing the area per unit time. So here we written down the volume occupied by the liquid in time dt. So now if we put dt equals to 1, that means unit time. So this one basically gives the rate of flow. Okay. So then this one becomes v ds, right. We put unit time dt is 1. Okay. So which is represented the flux of liquid flowing across the plane, that means across the surface ds. Okay. So in case of tilted surface, this one is v ds cos theta, right, v ds cos theta in general. Okay. In general, so which is represented the flux of liquid flowing across the plane or across the surface. Okay. Across the surface. Okay. So this is the flux in case of liquid. So in general, this vds cos theta. So if we written in terms of in form of vector, okay. So then this one becomes v vector dot n cap ds. Okay. Basically, the n cap is the area vector. Okay. N cap. So n cap is the area vector. Okay. So say that the ds vector is n cap times ds. Okay. So this is the area vector. So for 2D surface, area vector is always perpendicular to the surface. Okay. Perpendicular to the plane, because if we consider a 2D surface in a plane. Okay. And that's why this one is a n cap. Okay. So next, so in case of electric field, instead of fluid, electric field, we define an analogous quantity called electric flux. So we define an analogous quantity called electric flux. So in this case there is a no flow of physical observables. So in the previous case we consider the flow of liquid and calculate the flux, okay. But in case of electric field we define the similar kind of quantity that is called electric flux, but this is not a consequence of some flowing physical observables, right. So in this context we consider the electric field lines. So in this context we consider the electric field lines, that means the number of electric field lines crossing a unit area, okay, placed normal to the field directions. So instead of liquid in the previous case we consider the electric field lines in this case, okay. So this is not a physical observables. So electric field lines and then the number of electric field lines crossing a unit area number of crossing a unit area placed normal to the field directions, similarly as before, normal to the field direction at a point each measure of the, so where we place this surface, okay, or the volumes. So at a point is a measure of the strength of electric field at that point, okay, is a measure of the strength of electric field at that point. So basically that is the number of electric field lines crossing a unit area, okay, placed normal to the field directions, okay, and if this surface will be placed at a point where we measure the strength of the electric field. So if we consider a small planar surface dx, okay, and the electric field line crossing it is proportional to, so if we consider a, let us say this one is a electric field lines similar to the liquids, okay. So the E vector, okay, and we consider a small surface delta S, okay. So this is the delta S. So the electric field line crossing it is, I mean through the surface is proportional to, so electric field lines passing through the surface delta S is proportional to, okay, so E delta S, I mean the strength of the electric field at that point where the surface is present, okay, and times the area of the surface A, okay, so is proportional to E delta S. So now if we consider a closed surface, okay, so here we consider a planar surface, that means the area vector is perpendicular to the surface, okay, ds vector or del s vector. So if we consider a closed surface, okay, so every area element of the closed surface is taken to be the directions of the outward normal, okay. So that means so if we consider a closed surface, let us consider a sphere, okay. So this one is a closed surface and the area element, if we consider a small area element on the surface of the sphere, so it is always taken to be in the direction of the outward normal. So n cap is always directed to the r cap, okay, and theta is the angle between the outward normal and the electric vector, okay, E. So if we put in the electric field, let us say in these directions and place the sphere on that. So the angle theta is here, okay, in case of closed surface, and this one is a open surface, okay, this one is open surface. So therefore the electric flux delta phi, electric flux delta phi through an area element delta S through an area element delta S is defined by delta phi E dot delta S, right. So this one is E delta S, in general cos theta dependence, right. So cos theta, and what is the unit of this flux? So this flux is delta phi for a area element delta S. So if we consider total flux over the whole surface, okay, we have to add all the small elements, okay, considered in the surface, okay. So I will come to this point. So what is the unit of flux? The unit Newton Coulomb inverse meter square, right. Since E, what is the unit of electric field E? It's Newton per Coulomb, right, and what is the unit of delta S is meter square, right. So we consider a surface, not volume, okay. So we calculate the total flux. So basically divide the surface into a small area element and calculate the flux at each element, okay. So we know the flux of a small area element ds, okay, this delta phi is E times ds, okay, and that is why we define for a small area element delta S. Now if you calculate the flux through an whole surface, we first split this surface into small elements, okay, and we know that what is the flux for a small area element, and then we actually algebraically add up, okay, for all area element. So therefore the total flux, so therefore the total flux through a surface S is phi is approximately, why we consider this approximate, I will come to this point. So sum over E dot delta S vector, right. In the delta S tends to 0 limit, tends to 0 limit, we know that the sum delta S, sum over delta S becomes integral, right. So here why we use the approximate sign here, since we consider the electric field is taken to be constant at the small area element, okay. So over the whole area element delta S, we consider the electric field is constant, but this one is not true, right. So in the limit delta S tends to 0, okay, which is consistent, the electric field is constant in the limit of delta S tends to 0. So that is why we consider delta S tends to 0 limit at the end, okay, and then the sum becomes an integral. So in the next class we will calculate, so we consider a sphere and calculate the electric flux, okay, passing through this sphere, okay. So we will see in the next class. Thank you.